So, hi guys, welcome to Geography series, lesson 3. In today's class, we are going to learn about distribution of continents and oceans. Okay, in previous classes, we have learned about latitudes and longitudes, and after that, in second class, we have learned about origins of the universe and evolution of the Earth. Okay, um, before jumping into interiors of the earth, the earthquakes and volcanoes, we have to learn about how continents and oceans are formed, and after that we will learn about interior of the earth. Okay, in today's class, I will divide this chapter into two sections. In today's class we will learn about uh, continental drift theory, and after that convectional current theory, and after that seafloor spreading. Okay, in tomorrow's class I will teach about not tomorrow, next class I will teach about plate tectonics and how Indian plate is formed. Okay, yeah, and let's start. Before learning about distribution of continents and oceans, we have to learn a little bit about interior of the earth, not in detail but a little bit. Okay, yeah. In second class, I have taught you that how Earth layers are formed from core to the crust, depending on their densities. It got divided from core to the crust. Okay, we will learn about. I will name those layers, and because those names appear in between this concept, so that's why I'm explaining it to you. In chapter called Interior of the Earth, I will explain in detail how scientists discovered these layers and how these layers are formed, what is the constituents of these layers, what is the distance of these layers and all. Okay, at present I will just teach you the names and definitions of them. Okay, yeah. The uppermost layer is called as crust. Okay, crust, and below this crust we have mantle. This is crust. Okay, and below the mantle, at the core, that is at the center, below the mantle, that's way below, we have core. Okay, yeah. Crust is of okay. How do you imagine this figure? You imagine this figure as an inverted cone like this. Not inverted, it's just a cone. Uh, it is cross section of the earth. What is cross section? For example, if you take a watermelon, imagine this is a watermelon. Uh, yeah, you made cuts like this in middle. Okay, you made a cuts like this, and you took out that part. You took out that part, this part. Okay, you made a cut like this in a rectangular shape, and you took out that part. How it will look like? It will look like something like this. Okay, this is the outer part, the green color part, and this is the fruit part. Okay, similarly, so this is cross section of a watermelon. Similarly, if we take a cross section of a earth from, imagine this is a earth, this is upper layer. You made cuts here, and you took that part from that is from the uh, upper part to the central part. And if you took a cross section like that, you have uppermost crust. Oh, sorry. You will have uppermost crust part, and below this fruit part, imagine this is a fruit part of the watermelon, and this fruit part is divided into two: mantle, and at the center there is core. Okay, yeah. Now crust is divided into two parts: continental and oceanic. Yeah, uh, continental is thicker compared to oceanic crust. Oceanic crust is denser compared to continental crust. Okay, The thickness of the continental crust varies somewhere around 30 kilometers, and thickness of the oceanic crust varies from about 5 kilometers. And the thickness of the continental part might go up to 70 kilometers in areas like huge fold mountains like Rocky Mountains or Himalayas. Okay, yeah. Now, difference between thickness and dense. Thickness means it is more in area. Okay, it is very thick. It is very bulge. Okay, compared to the continental crust, oceanic crust is less thicker. That is, it is less bulged. Okay, less area. But oceanic crust is denser. Even though it has a less area, even though it has a less thickness, the amount of particles concentrated in a particular unit is more compared to continental crust. Okay, if you take, this is oceanic crust. Okay, and this is continental crust. Okay, it is made of some materials, right? Uh, and when it comes to oceanic crust, if you take a particular section in ocean, that is this section. If you took this section and you took this section, yeah, there are yeah, let's say it's section A and it is section B within oceanic crust. Section A, and within continental crust you took section B. Okay, the number of areas are similar. Both A and B are similar in area. Okay, you took two sections from oceanic and continental crust. The two sections are similar in area. Okay, the number of particles concentrated in A are much more compared to number of particles concentrated in area B. Okay, that means concentrated means in sense present. Okay, the particles present in A are more compared to particles present in B. So on a whole, we can say that A is much denser than B. Okay, now it made sense to you why oceanic crust is denser than continental crust, because the number of particles concentrated in a particular unit of area in oceanic crust is much more compared to continental crust. Okay, this is the reason why oceanic crust is much denser than continental crust. Okay, on contrary, continental crust is much thicker than oceanic crust. Why? It is much thicker. It is much more in area. Why? Because continental crust is made up of huge number of deposits. Let's take imagine this is a continent. Okay, I mean boundary of a continent. In a continent we have many mountains, many fields, soils, like that. Yeah. Um, many rivers cut through these mountains. There will be huge amount of rainfalls. Okay. These rivers, this rainfall disrupt the material from those physiographical features. That means disrupt the material, that they take away the material from those mountains, fields, plains, etc. And they all concentrate here. I mean here in the sense at the coastline. Okay, or somewhere in the continental area. They get deposited in certain area. Okay, that's why it is much more thicker, and there is no this kind of deposition that does not happen in oceanic floor. Okay, the main source of deposition for oceanic floor is these sedimentary rocks from continents and volcanoes that are erupting from interior of the earth. We will talk about it. Okay, so the materials depositing in continental crust is more compared to materials getting deposited in the oceanic crust. That's why continental crust is much more thicker than the oceanic crust. Okay, yeah. After the crust we have mantle. Mantle is divided into upper and lower mantle. Okay, upper mantle, it is how would I say that, it is viscous in nature. Viscous. Okay, lower mantle is solid in nature. Viscous is nothing but it is a state between a liquid and a solid. Okay, it is viscous, that is it is much more fluid in nature, like a jelly. Okay, it is viscous. like a gel. It's not a complete solid. It is viscous in nature. Okay. This upper mantle is called as asthenosphere. Astheno means weak. Weak in the sense it is not a solid. Okay, it is not a solid. It's not a it's not compact of compact like soil solid, but not as how would I say that, not as loose as a liquid. Okay, it is weak in nature like a jelly. Asthenosphere, we call it as asthenosphere. Okay, crust plus asthenosphere or upper mantle is together called as lithosphere. Okay, yeah. After the mantle, we have core. Core is outer and inner. Okay. Uh, Outer core is liquid in nature. Inner core is solid in nature. Yeah. This is about layering of the earth, interior layering of the earth. Okay, from upper surface to the center, crust, mantle, and core. I will explain about it in detail in the next chapter. Okay, please don't worry. I have set these definitions so that you'll understand the next part coming in this chapter. Okay. Now let's get into distribution of continents and oceans. Um, there is a meteorologist called as whose name is so not called as whose name is Alfred Wegener. Okay, Wegener. He is a meteorologist. He was the first scientist who put forth the idea or who came forward with the idea of drifting of the continents. That he said that continents and oceans moved apart. The continents and oceans we are seeing today, they are as a result of drifting. Okay, he said following factors were responsible for the drifting of the continents. We learn what Alfred said. Okay, Alfred said that many thousands of millions, thousand million years back, Earth was like this. It is a sphere with huge landmass called Pangaea, surrounded by huge ocean called Panthalassa. This is the, this is called Pangaea, and this is called Panthalassa. Also, the southern tip of Pangaea is called as Durban. Durban is southernmost tip of Africa present day. Okay. What did he say? Initially, um, uh, all the continents were a single unit called as Pangaea, surrounded by large oceanic mass called as Panthalassa. Okay. Eventually, due to a force called polar fleeing force, I will explain it. Wait. Polar fleeing force, Pangaea started moving towards equator. Okay, Pangaea started due to polar fleeing force. Pangaea started moving towards equator, and it got divided into Laurasia and Gondwana. Okay, it got divided into Laurasia and Gondwana, and in between them there is Tethys Sea. What was the force responsible for equatorial movement of the Pangaea? It is polar fleeing force. Okay, what is polar fleeing force? Uh, Due to rotation of the Earth rotates from west to east. Okay, due to rotation of the, we'll talk about rotation, revolution, and all during climatology. We will talk about it in detail. Okay, why rotation is still happening, why rotation is happening. We'll talk about it in climatology. Okay, At present, you just learn that due to rotation of the Earth, due to west to eastwards rotation of the Earth, uh, yeah, due to west to eastward rotation of the Earth, Earth is flattened at the poles and bulged at the equator. It is flattened at the poles and bulged at the equator. Okay, due to the rotation, the west to eastwards rotation, Earth is bulged at the equator and flattened at the poles. Okay. And just now we have learned that the interior of the Earth contains crust, mantle, and core. As we move towards from crust to core, the density of the material increases. Okay, the density of the material increases. The core, as the poles are flattened, the core is much nearer to poles. Okay, and far away to equator. Okay, due to the geoid shape of the Earth, that is flattening of the poles and bulging at the equator, the core is much nearer to poles and far away to the equator. Okay, uh, this results in higher gravitational attraction at poles due to the proximity of core towards the poles. That means core is much nearer to the poles. There is high gravitational attraction at poles. High gravitational attraction at poles. Why high gravitational attraction at poles? Because of the proximity of core. Core is very dense in nature. Okay, that means it has more weight. If something has a more weight, it will have a tendency to attract uh, materials or objects that were lesser in weight. Okay, due to it has a high gravity. Whenever a material is dense in nature, it has high gravity, and it has a tendency to attract materials that were less dense than this. Okay, so that's why, though as it is nearer to the poles, gravitational attraction is more at the poles. Due to that gravitational attraction, high gravitational attraction at the poles, Pangea started drifting towards equator. Pangea is at the polar region, and due to polar fleeing force, what is polar fleeing force? The high gravitational attraction at the poles is called as polar fleeing force. Okay, it attracted the Pangaea located at the southern end of the Earth towards the equator. Okay, and the polar fleeing force acted at both northern and southern hemispheres. Okay, this is what other Alfred Wegener said. Okay, the polar fleeing force is at both north and the south. Okay, that's why Pangaea got divided into Laurasia and Gondwana. Okay, after this, what happened? After this, wait. After the division of Pangaea into Laurasia and Gondwana, now other Alfred Wegener came with another force called as tidal force. Due to tidal force, the continents started drifting westwards. Okay, Laurasia and Gondwana, due to tidal force, they started drifting towards westward. Okay, and due to this westward movement of the Laurasia and Gondwana, uh, westward movement of the Laurasia and Gondwana, Laurasia got divided into North America, Europe, and Asia. Okay, due to westward drifting of Gondwana, Gondwana got divided into South America, Africa, India, Australia, and Antarctica. Okay, due to westward movement of Laurasia, Laurasia got divided into North America and Europe with North Atlantic Ocean between them, and Asia. Okay, uh, Gondwana got divided into South America and Africa with South Atlantic Ocean between them, and uh, and into India and Australia with Indian Ocean between them, and Antarctica. Okay, due to what is the force that was responsible for the westward movement of the continents? It is tidal force. Okay, what is tidal force? We all know that Earth revolves around the sun. Okay, Earth revolves around the sun, and Moon revolves around the Earth. We all know that. During this revolution, uh, at certain points of time, Earth will be closer towards the Moon, and at certain points of time, Earth will be closer towards the Sun. Okay, whenever Earth is closer towards Moon and Moon or Sun, the oceanic mass, like the oceans in the on the Earth started will start rising. Okay, this is Moon. Let's say this is Moon, and this point of time, Earth is nearer to the Moon. So this entire part of the Earth, which is under the influence of the Moon, which is under the influence of the Moon, uh, will start rising. Okay, the oceanic mass, which is under the influence of the Moon at that point of time, will start rising. It is called as tide. The high rising of the ocean due to gravitational attraction of Sun and the Moon is called as are called as tides. Okay, when our Moon or Sun is far away from the Earth, the oceans experience low tides. Whenever they can, they means in the sense Sun and the Moon can influence their gravitational attraction towards the Earth. We see high tides. Okay, due to this high tides. Okay, there is application of force called tidal force due to high tide rises, and this tidal force is responsible for the westward drifting of the continents. Yeah, this is what Alfred Wegener said, and not only he not only explained about drifting of the continents and oceans. He also talked about how fold mountains and islands are formed. This is how he said that during westward movement of the continents. Okay, whenever the continents is drifting towards westwards, the frictional force between oceans and the continents led to the rise of a series of mountains called as folded mountains. Okay, he said that when North America is getting separated from Laurasia due to the friction of eastern coast of North America and the Atlantic Ocean, Rocky Mountains are formed. Okay, and whenever when Gondwana, when it is Gondwana, when Africa and South America got divided due to tidal force, the friction between South Atlantic Ocean and South American West Coast, um, Andes fold mountains are found along the western coast of South America. Okay, and my serious suggestion is whenever from this chapter onwards, yeah, make sure you keep your atlas while listening to the class. Keep your atlas open. Uh, I don't know whether you're making notes or not. I think there is ample amount of time in the class itself to make running notes. And while you are revising, please look at the places I'm talking about. Up to now, I have talked about a place called Durban. I said that it's at tip of the Africa, and now I spoke about Rocky Mountains. Locate them on your map. I spoke about um, Andes Mountains. Locate them on your map. Even continents also. Okay. I spoke about Europe, Asia, North America, South America, Africa, India, Australia, and Antarctica. Locate them on your map. Uh, how locate in the sense see whether they are at the equator or they were closer to poles or they were closer to Tropic of Cancer or Capricorn. If I say Rocky Mountains, just look where these mountain ranges lie, in which latitudinal range these mountains lie. I think above 30 degrees north latitude, I think so. Just look at it, and we have learned about torrid zones, temperate zone, frigid zone. Just see if the places I am talking about, whether they fall under torrid zone or temperate or frigid zones. Okay, see whether Andes falls in which heat zone or which latitudinal range. Okay, see whether Rocky Mountains fall in their temperate zone. Yeah, just look at it. Okay, while revising and or while listening to the class. uh, what happens is, if you look at map continuously or thoroughly, if you look at places on the map, you get accommodated with the map. Once you get accommodated with the map, you can visualize it in your brain while studying geography. It's really helpful. Okay, try to locate places on the map. Okay, locate in the sense, just now said, make sure those places are near the equator, or in which heat zone they fall under, which latitudinal zone they fall under, which hemisphere they fall under. Make sure you locate them and revise them thoroughly and memorize them. Okay. Yeah. Where were we? Yeah. Westward, during westward movement of the westward movement of the continents, due to friction between the underlying ocean and the continent, fold mountains are formed. Okay, this is how Alfred said how mountains are formed. He also said how islands are formed. Okay, he said that when continents are drifting westwards, the tidal force responsible for the westward drifting of the continent is not strong enough. As it is not strong enough, some parts of the continent that is drifting got separated, and they they lie as islands. Okay, that is why all the islands lie to the eastward of the of a country or a continent. Okay, uh, if you clearly observe, the Caribbean islands are towards east of the North America, and Philippines islands and Sumatra, Java, Malaysia, Indonesia, they were all towards the right side of the Asia. Okay, right side of the Asia. Okay, why? Because according to Alfred Wegener, during westward movement of the continents, the tidal force responsible for the westward drift was not strong enough, so that certain parts of the continent got separated and they remained as islands. Okay, this is what Alfred Wegener said. What were the forces that were responsible for drifting of the continents according to continental drift theory by Alfred Wegener? They are tidal force and polar fleeing force. Remember this. Okay. Not only this, even Alfred Wegener gave certain evidences for his continental drift theory, and those evidences were they were highly appreciated by the fellow scientists, and they were proven to be very accurate even to the present. Okay, let us learn about those evidences. There are certain evidences given in 11th class physical geography chapter 4. I will teach about them. Okay, the first evidences for continental drift. First one is jigsaw fit. Jigsaw fit of continents. Uh, what is jigsaw fit? Jigsaw fit means if you take two uh, two materials. Okay, let us imagine this is one material and this is one material. Okay, the boundary of this material, the boundary of this material and boundary of this material are in same configuration. Okay, same configuration means if these materials, if you join these two materials, they will fit each other in a precise manner. Okay, in jigsaw fit, if you take two materials, they have same outline configuration, in such a way that if we try to fuse these two materials, they will fit in a precise manner. This is called jigsaw fit. Okay, there is jigsaw fit for you said that there is jigsaw fit for continents. What Alfred Wegener said, if we look at eastern coast of North America and west coast of Europe, uh, they were the coastline is much more similar. The coastline of east coast of North America and western coast of Europe, they were much similar. That if we join together, they will fit. And moreover, the eastern coast of South America and west coast of Africa were also um, similar in nature, so that if we try to fuse together, they will fit. Okay, and later on, the maps developed by the cartographers, they vouched for this theory, jigsaw fit theory, and said that yes, Alfred Wegener is right. You just locate on the maps, okay, the east coast of South America and west coast of Africa, they will be in similar way. Okay, and this proves that they they were due to jigsaw fit theory. We can say that these two continental masses were together at certain point of time. This is one evidence. Okay, another evidence is rocks of same age across the ocean. Okay, uh, if we there's a there's a technical radio dating. Okay, using this radio dating, scientists will determine ages of the rocks. They'll determine how millions of years they are formed. Millions of years back they were formed. Okay, due to this radio dating, scientists found that the rocks along the eastern coast of Africa, Brazilian coast, and rocks along the western coast of Africa, they were of the same age. Okay, these two continents were almost thousands of kilometers apart, with South Atlantic Ocean between them. And scientists have found that the rocks on the Brazilian coast and rocks on the western coast of Africa were of the same age, indicating that these two continental masses were together at certain point of time. Okay, this is one evidence. Another one is tillite. Tillite means you all know about wait. I'm sorry. The second one is rocks of same age across ocean. Okay. Third evidence is tillite. What is tillite? Uh, we all know about glaciers, Himalayas, Swiss Alps. These are glaciers. Deposits from these glaciers. The deposits can be formed through landsliding or rainfall or water. The deposits from these glaciers is called as a tillite. Okay. Um, is called tillite. These tillite in a Gondwana system, that is that these tillites in Gondwana system, that is I mean India, the tillites in India, the same similar tillite was found in six landmasses in southern hemisphere. India is in northern hemisphere. Okay, and um, that the tillite that was found in India is much more similar to the tillites that were found in landmass of southern hemisphere. There are six landmasses where the similar tillites are found. It is from okay. I will read it from NCRT. Okay, those places were Africa, Falkland Island, Madagascar, Antarctica, and Australia. Okay, the tillite evidences found in India were much more similar to tillite evidences found in Africa, Falkland Island, Madagascar, Australia, Antarctica. Okay, indicating that these five land masses, and India were together at certain point of the time. They were all one place at certain point of time. That means Gondwana. They are all together as a Gondwana at certain point of time, and later due to certain forces they got divided. And this is evident to the tillite evidences found in India and these five land masses. Now, I have said that certain places like Falkland Island, Madagascar, okay, Africa and Australia, all know that. Falkland Island, locate Falkland Island in your map. It will be on southern tip of South America. Falkland Island is important in geography perspective because it is a fishing zone. Okay, and Madagascar is also important due to its you know biodiversity. Madagascar is also important. Please do look at Madagascar will be on eastern coast of Africa. Okay, look at these two places on your map: Falkland Islands and Madagascar. Okay, and till later. Another evidence is distribution of fossils. Okay, there is a primate called as lemur. Primate means ape. It's a monkey. Lemur. Fossils of lemur were found in India. Okay. Surprisingly, lemur is not native to India, but its fossils are found in India. Okay. But lemur is originally native to Madagascar. This indicates that these two land masses were together at certain point of time. Okay. These are the evidences given by Alfred Wegener. Okay. Scientists have highly appreciated Alfred's approach towards drifting of the continents and evidences given by him. But scientists after First World War and Second World War they disregarded Alfred Wegener's reason behind drifting of the continents. He was correct about drifting of the continents. Okay, the evidence given by him or theory part given by him is correct, but scientists disregarded the forces that were responsible for the drifting of the continent. Okay, what Albert Wegener said, he said that uh, tidal force and polar fleeing force were responsible for drifting of the continents, but after First World War, after First World War discoveries and researches, scientists said that they might not be the forces responsible for the drifting. Then scientists proposed there are certain endogenetic forces that happen in interior of the Earth, and those forces were responsible for the drifting of the continents. Okay, they also disregarded uh, what uh, Alfred Wegener's theory about formation of mountains and islands also. Okay, what were the discoveries after this drifting? This drifting theory proposed after continental drift theory proposed by Alfred Wegener. There are certain studies happened, and what were those studies? We look into it. First and foremost is convectional current theory. Okay, it was proposed by Arthur Holmes. Convectional current theory. It was proposed by Arthur Holmes. Do you know what is convection? Okay, uh, convection is nothing but if you heat a certain material, it can be a liquid or a solid part. If you heat it, um, the uh, the one which is heated more will try to move upwards. Okay, it will try to move upwards. It is called convection. Why it tries to move upwards? Once a material gets heated within a fluid, convections happen within a fluid, not solid. Okay, I'm sorry. Convections happen within a fluid. If you heat up a fluid, the heated, the heated, the heated material within that fluid tends to move upwards. Okay, and the colder part, that means less heated parts, lie in the bottom. Okay, why this more heated part tries to move upwards? Because whenever you heat a material, it develops a tendency to cool down. Okay, because the molecules inside it will be in excited state. Okay, no atom, no atom will be in excited state. Every atom tries to be in a I don't say dormant state, in a steady state. That's why bonds will form. Chemical bonds. Why chemical bonds happen? Because atoms have a tendency to stabilize. Okay, through bonds, they either donate or they either donate or receive electrons, and they stabilize. Whenever you heat a material, it develops a tendency to stabilize. In that on that due to the tendency to stabilize, it start moving upwards to cool down. When if it's cool down, it will stabilize. Okay, so this is called convection. It is convection is nothing but it is a tendency of a heated material within a fluid to stabilize or to cool down, to move upward. Okay, this is called convectional current theory. What other Holmes said that uh, the below the below the earth, uh, due to radioactive elements, there is heating happening. Okay, we have talked about asthenosphere. Okay, within the asthenosphere, it is the material of asthenosphere is called as magma. Okay, okay, magma. There is heating of magma inside the earth. Why heating of magma is happening? Due to radioactive decay. The radioactive elements, they are getting decayed, and while getting decayed, they emit energy in the form of heat, and this heat is making asthenosphere volatile, and as the fluid is getting heated, as the fuel is getting heated, it will develop a tendency to move upward. Okay, move upward. It is called convection. It is developing a tendency to move upward. Okay, I will explain in detail. See, this is crust. Okay, this is crust. Below the crust we have mantle, upper mantle. What upper mantle consists of? Upper mantle consists of magma or asthenosphere. Due to radioactive decay, there are radioactive elements here. Due to radioactive decay, that is, the elements are getting decayed and they're emitting energy in the form of heat, and this energy is heating up the magma. Okay, then what happens? Then magma starts rising upwards. Okay, magma is started rising upwards, and by rising upwards, it is developing cracks in the crustal part. Okay, it is developing cracks in the crustal part. Okay, develops cracks in the crustal part. Okay, when it is hitting the crustal part here, this rising magma has hit at the crustal part and it's getting diverged like this. Okay, and here also there are radioactive elements. Here also, oh, I'm sorry. Here also there are radioactive elements. Okay, here also decay is happening. Uh, in this area also there is rising magma. Okay, it hits the crustal part and develops cracks here and gets diverged. Okay, here see, it is getting diverged here. Here it is getting diverged. It hit and got diverged. It hit got diverged, and this magma is is also converging with magma coming from another direction. These two are converging and settling down. Okay, and again it is getting heated due to decay and rising up. So we can see a cycle here. It is called as convectional current. Okay, this cycle is called as convectional current. Okay, due to radioactive decay, magma is rising up, hitting the crustal part, developing cracks on the crustal part. It is getting diverged, Okay, this divergent magma is meeting with another diverging part of the magma. They got converged together, and they are moving down. They got converged and moving down. While moving down, they again getting heated up and rising, and this cycle continues. This is called as convectional current theory by Arthur Holmes, and it is happening in the interior of the earth. Okay, he said that due to this convectional current theory, the magma is hitting the crustal part, developing cracks, and it acts as a responsible force. This convectional current acts as responsible force for the separation of the plates. Okay, the convectional currents hit the crustal part. Continuously, the heating is happening, cracks were developing, and through these cracks, this hot magma oozes out in the form of lava and get deposited on the crustal part, that is on the surface of the earth. We'll talk about it later. And for now, you all I hope you understood what convectional current theory is. You understood this cycle, right? Getting decayed, emitting energy in the form of heat. So magma rising up, hitting the crustal part, diverging, and again converging with the another diverging part of the magma. They both reach down, again get heated up, and again rise towards the crustal part. This is called convection. This cycle is called as convection current, and it is happening interior of the earth. It was proposed by Arthur Holmes, and these convectional currents were responsible for the movements of the continents. It is hitting, so that the due to that forceful hitting, cracks were developed and continents are getting separated. It is proposed by Arthur Holmes. It is called convectional current theory by Arthur Holmes. Later, based upon the studies proposed by Arthur Holmes, uh, a scientist called Harry Hess proposed sea floor spreading. Okay, yeah. Let us talk about sea floor spreading. Initially, we said that the whole continent existed as Pangaea, and later Pangaea got divided into Laurasia and Gondwana. Okay, uh, it we said that it got divided again. Laurasia got divided into North America, Europe, Asia. Okay, if we say that something is dividing, it's getting separated, right? It's spreading apart. It is spreading apart. Is it that continents are spreading apart, or the underlying parts it's getting separated, and it is acting as a reason behind the drifting of the continents? Okay, just follow through, and let me explain again. The continents are getting separated, right? They are getting separated. They're spreading apart. Is it that continents are getting separated, or is there any other floor or lying mass I mean beneath the continents that is getting separated? Beneath the continents, we have oceans. Okay, according to Harry Hess, based on the conventional theory of Arthur Holmes, the sea floor is getting separated. I mean, that is spreaded due to rising of magma. It's hitting the oceanic crust, and oceanic crust is getting separated, and this separation led to the spreading apart or drifting apart of the continents. This is okay due to sea floor spreading, continents are drifting apart. Okay, this is called sea floor spreading. It was proposed by Harris. Okay, what is sea floor spreading? He actually said, if you locate on the map, um, just see North Atlantic Ocean and South Atlantic Ocean. Okay, you can see a series of white patch running from almost uh, from England coast or above northwards of England, Norway coast to almost Falkland Islands. There is a series of white patches you can see. These series of white patches are nothing but mid-oceanic ridges. We call them as mid-oceanic ridges. They are volcanic eruptions. we'll call them as mid-oceanic ridges. They are volcanic in nature. That means they are active. When I say they are mid-oceanic ridges are active, it means that the magma is still rising and oozing out. Okay, the magma is still rising from the oceanic crustal part and oozing out as lava. And these ridges are formed as a series from in North and South Atlantic Ocean. Okay, these are called mid-oceanic ridges, and you can look at these white patches in many oceanic masses. You can see East Pacific rise. They are also mid-ocean. They are also called as oceanic ridges. Give me a minute. Okay, these are called oceanic ridges, and also you can see white patches along the coastlines on along the North American coast, somewhere around Canadian coast and North American coast, East Coast, and at Alaska part, you see white patches along the coastline. These white patches are nothing but they are continental shelves. We call them as continental shelves. They consist of materials that get deposited from the continent. Continent due to rivers and rainfall, the materials from the continents got deposited in the coastal areas, that is shorelines, and this deposition is called as continental shelf. Okay, and the white patches that we see in middle of the ocean, that East Pacific rise, and in the North Atlantic and South Atlantic Ocean, they are called as mid-oceanic ridges. Okay, what did seafloor spreading say? And yeah, before that, I will explain what seafloor spreading means. Okay, yeah. Imagine this is a continental mass. This is a continental mass. Okay. Uh, Initially, these two continental masses were together. Okay, these two continental masses were okay. This is better. Were together. Okay. Imagine this is the okay. This is the part, and this is magma from the interior of the earth. This magma has hit at the continental part. I mean the uh, crustal part. Okay, and developed cracks and started oozing out lava. Whenever it started oozing out lava, they got slightly separated. Okay, and this series of hitting and oozing out resulted in the drifting apart of the continents. Okay, drifting apart of the continents and an ocean between them. How ocean is formed? Initially, there might be a depression has formed, and this depression got filled by deposits and rainwater, and the ocean is formed. Okay, we are not concerned about it. These are two continents that were together due to hitting of the magma from the behind. Cracks are developed. Through these cracks, the magma traveled and oozed out as lava. Okay, and due to that hitting and oozing out, continents got separated. This heating and oozing out happened at sea floor and it got separated. Further heating and oozing out separated. Further heating and oozing out separated. And that's how uh, two continents with ocean between them are formed. For example, you look at North America and Europe. They got separated with North Atlantic Ocean between them. Okay, I said that the magma is hitting and oozing out lava. This magma hitting and oozing out lava happened over a period of time, and these mid-oceanic ridges were formed. Okay, so now this is two continental masses. What happened? And from these continental masses, we can see sediments. How sediments are formed? Due to rivers and rainfall, the materials from the continental mass get deposited on the shoreline, and these sediments are formed. Okay, and there is rising magma and this rising magma oozed out in the form of lava, okay, and formed volcanic mountains in middle of the ocean. Okay, this rising magma is hitted the oceanic crust part and oozed out, forming a series of volcanic mountains. Okay, whenever I say series of volcanic mountains, I said that the magma is hitting the crustal part, and crustal part is developing certain cracks. Okay, eventually, after a long period of hitting, these cracks get opened, and magma is traveling through those opening of the cracks and getting deposited on the crustal part on either side. Okay, wait. Initially, the crust was like this. The magma is hitting. There were cracks open and oozing out and forming a rock here. Okay. When it is happening, I have said that it is after a series of hitting, continents got separated. This might be the reason. Recent rock, it might be a recent rock because it was towards the ocean. When we travel from ocean towards the continent, there will be a series of rocks like this. Okay, series of rocks like this. Uh, how these series of rocks are formed? Again, coming to the same point. Initially, continental masses are together. Okay, magma is hitting from the bottom and oozing out. Okay, opening up the crustal part, developing cracks and opening it up, and traveling as lava and oozing out and getting deposited. Okay, it is the first rock that gets deposited. It is the first one. When these two continental masses, when they were together, this is the first one it is formed. That means it is much older. Okay, due to series of such events that they have drifted apart, and uh, first rock these rocks were formed. After that, further oozing out of lava was formed. Um, I mean, beside it, another one was formed. This is the second one that was formed. Okay, these were the first ones that were formed. They were very much older because they were formed when the continents were together, oozed out and formed. That means the rocks that were towards the continents were much older, and rocks that were if you move from continents towards the ocean, these ridges or these rocks, their age gets younger. The older ones were on the continental side, and the younger ones were at oceanic side. Younger. Okay, as we move from continents towards the ocean, the ages of the rocks decreases. As if we move from ocean towards the continents, the ages of the rocks increases. Why? I have just explained. It is because of the sea floor spreading. Initially, they were together, hitting of the magma. These got separated, and a rock got formed here and here. This was the first rock that got formed. Again, hitting happened. Okay, they were further drifted, and another rock were formed. Series of rocks were formed. Okay, drifting happened, rocks formed. Drifting happened, rocks are formed. So the older ones were at the continental side, and as if move from continents towards the ocean, that is from here to here, the ages of the rocks gets decreased. Okay, this is how seafloor spreading has happened. Okay, why is it? The reason behind seafloor spreading is convectional current theory proposed by other Holmes. That is due to radioactive decay, the heat is generated. Due to that heat, the magma started rising upwards and developed cracks on the crustal part and start oozing out as lava. Due to that cracks and developing of the cracks, the crustal part got separated and lava oozed out. Okay, uh, and you have understood this concept of seafloor spreading. And Harry has said certain, there is a theory part for the seafloor spreading. I will read it out from NCRT and I will explain it to you what each statement means. Okay. What Harry has said that the concept of seafloor spreading has the following facts. Okay. Fact number one. It was realized that all along the mid-oceanic ridges, volcanic eruptions are common and they bring huge amounts of lava to the surface in this area. Okay. What he is saying, all along the mid-oceanic ridges, we have talked water mid-oceanic ridges. Okay, there is a series of white patches in the oceans. They are called as mid-oceanic ridges. Okay, volcanic eruptions are common at mid-oceanic ridges. Why volcanic eruptions are common at mid-oceanic ridges? The magma is rising from the interior of the earth and it is oozing out from those ridges. Ridges are nothing but they are mountains. Okay, they are um, uh, as it is getting developed, it will be a huge area. It looks like a mountain. They are called as ridges. Okay. They are active in nature. Active means there is eruption still going on there. Volcanic eruption still going on there. New material is getting deposited at those ridges area. Okay. The first one. Second one. The rocks equidistant on either side of the crust of the mid-oceanic ridges show remarkable similarities in terms of period of formation. I said these are the rocks. Okay. What the statement is saying, the rocks equidistant on either side of the crust of the mid-oceanic ridges. Crust means summit. Okay. The peak of a mountain is called as a crest. As it is oozing out, it is oozed out, and a rock is formed here because of the oozing out of lava. A rock is formed here. A rock is formed here. Hmm? The rocks equidistant on either side of the crust of the mid-oceanic ridges show remarkable similarities. Why they show remarkable similarities? Because they're formed on the same age, at the same age. Okay, at the same period of time. They both formed at the same period of time. That's why the rocks equidistant to the crust of the mid-oceanic ridges show similarities in terms of formation, in terms of chemical composition also. Why they're formed out of same magma? That's why they show similarities in chemical composition, and they the magma oozed out at the same point of time. That's why they also show the rocks equidistance on the either side of the ridges also show similarities in the time period of formation in chemical composition and magnetic properties also. Why? What do you mean by magnetic properties? Means uh, due to rotation of the earth, the materials inside the earth, that is the materials that have magnetic properties, they will align sometimes towards the north and sometimes towards the south due to rotation of that, and certain many other factors there, universal factors that's responsible for alignment of those magnetic materials. Sometimes they will align in northwards and sometimes they will align southwards. Okay, these just now we have talked that these rocks that are equidistant from on either side of the oceanic ridges, they show similarity in period of formation. They form the same period of time. That's why at that point of time, maybe the magnetic anomaly can be towards north or south. So they show same magnetic properties. They show same chemical composition. Why? They form from same magma. Okay, rocks closer to the mid-oceanic ridges. Rocks closer to here. The rocks. I am reading from NCRT. You also read from NCRT class 11, chapter 4, seafloor spreading concept of seafloor spreading. I have taught first point and we were middle on we were in the middle of the second point. Okay, we have talked about similarities of the oceans adjacent to the mid-oceanic ridges. Okay, and also the seafloor spreading is also saying that rocks closer to the mid-oceanic ridges are younger. Rocks closer to the mid-oceanic ridges are younger. As one moves away from the mid-oceanic ridges towards the continents, the age of the rock is increasing. Why? We have I just now I taught that due to convection current and development of the crusts, the separation of the continents, the rocks closer to the oceanic ridges are younger. and rocks closer to the, as we move from oceanic ridges towards the continent, the ages of the rocks gets increased, because rocks closer to the continent are much older. They were formed first during the first phase of separation. There are continuous phases of separation, subsequent phases of separation, and uh, uh, rocks away from the continent are younger. The surprisingly, the separation is happening still now. Okay, it is very at very slow rate, but it is happening. The continents are spreading even now also. Okay, because of the convection current that's going on in the interior of the Earth. So that's why new rocks will always form because of the lava or magma oozing out of those oceanic ridges. Okay, now coming to the third point. Ocean crust rocks are much younger than the continental rocks. The ocean, this rock one, two, they were, they are part of continental crust because they are adjacent to continent, and uh, they will be under the influence of continental shelf. Okay, because due to this sedimentation happening, they will be under the influence of continental crust because it is much thicker due to that sedimentation, and the rocks formed in the initial phase, that are older rocks, will come under the influence of the continental shelf. Then they will become the part of continental crust. And these rocks are rocks that are adjacent to oceanic ridges are much younger, and they come under the influence of oceanic crust. Okay, if you take the crustal part, uh, this is the continental crust, and this will be the oceanic crust. This is continent, and we are jumping into ocean. Okay, this is ocean, this is continent. Okay, crust means in the sense it is solidified part of the continent, solidified part of the ocean is oceanic crust. Okay, and it is all saying that the age of the rocks in the oceanic crust is nowhere more than 200 million years old. Some of the continental rock formation are as old as 3200 million years. Okay, the rocks adjacent to continental crust are as old as 3200 million years, and rocks adjacent to oceanic crust are not younger than 200 million years. Okay, that means imagine how much gap is there between the younger rocks and the rocks adjacent to continent. The rocks adjacent to continent were formed around 3200 million years ago. Okay, they are much more older than the rocks adjacent to oceanic crust. Okay, next, the sediments on the ocean floor are unexpectedly very thin. Scientists were expecting if the ocean floors were as old as the continents, they have a complete sequence of sediments for a period of much longer duration. However, nowhere was the sediment column found to be older than 200 million years. What is the reason for the sediments on the ocean floor? It is magma that is coming from the interior of the earth is the source of the sediments on the oceanic floor, because it is moving upwards and getting deposited on the ocean floor, and they act as sediments of the ocean floor. What scientists are saying, the sediments on the ocean floor are unexpectedly very thin. Why they are very thin? uh, I said that there is sedimentation happening at the continental part, continental crustal part, due to the sedimentary rocks. The due to this sedimentary rocks, the sediments on the continental part are more thicker. Okay, this kind of sedimentation or this kind of deposition of rocks is not happening on the oceanic floor. That's why sediments on the oceanic floor are thin. Next, the deep trenches have deep-seated earthquake occurrences, while in the mid-oceanic ridges areas, the quake foci have shallow depth. Okay, they have talked about trenches. Um, Trenches means, I think you all know that what trenches are. Trenches lie in the ocean, the deepest part of the oceans. Okay, I have said that when the magma hits the crustal part, they get diverged and again converge with an, oh, sorry, let me avoid that side. Okay, now this is crust. The magma that's getting it is hitting it and getting diverged. Okay, and also converging with another magma coming from another divergence. Okay, and getting and they are moving downward. Okay, while they are hitting it, the crustal part also moves either this side or this side. Okay, and also there is a crustal part in on other part of the earth, and this comes here. Okay, whenever a two uh, crusts converge, one of the crust subsides down. Okay, whenever two crustal parts converge, it is one crustal part and it is another crustal part. They both tend to converge. Why? Due to magma hitting it, the crustal part, and it's getting diverged. This diverging crustal part converge with another crustal part because they move due to the hitting of magma. Whenever they both converge, the crustal part which is more dense will subside down. Okay, the heavier part will subside down, and the lighter part will rise up. Whenever it is subsiding down, okay, um, imagine this is continental plate or crust. For timing, you remember it as crust. Plate. What is plate? We will explain in the next lesson. It is ocean, oceanic crust. They are both converging. Okay, let's say, how can I put it? Uh, yeah, okay. The Pacific plate, Pacific plate at the Philippines side is converging with Eurasian plate. Okay, ocean plate, continental plate. The ocean plate is much denser. We learned that ocean plate is much denser. It subsides down. Whenever ocean plate subsides down, but whenever ocean and the continental plate subsides down, there is a trench formed here. You can you see the V shape? It's subsiding down and say there is a deep thing is forming here. It is called as a trench, the deepest part of the oceans. Okay. What seafloor spreading is saying, the deep trenches have deep-seated earthquake occurrences. Earthquake occurrence. Earthquake occurrence means whenever magma is hitting that crustal part, the cracks are developed and Earth's getting separated, right? A quake is happening. A quake can be happened either by diverging or converging or through a slip. We will talk about it. Don't worry. Okay. And the foci, that means the focus point for this deep um, for trenches is deep seated. That means a trench part, uh, the hitting is happening at very deepest point, indicating that these trenches are very deep in nature. The crustal portion that is subsiding down is going very deep inside. Okay, and the focus point of the earthquake, where the magma is hitting, is very deep in nature. Where it is very deep, saying and it says that these trenches are very deep in nature. Okay, while in the mid-oceanic ridge areas, the quake foci have shallow depth. Okay, at mid-oceanic ridges, um, okay, at mid-oceanic ridges, um, this magma is hitting and oozing out. While it is hitting, it is getting separated. Quakes are formed, and the focus point of this quake is very shallow compared to the focus point of deep trenches. Okay. This is seafloor spreading. In this class, we have talked about Alfred Wegener's continental drift theory, which says that the whole continental mass is a single unit at certain point of time called as Pangea, and a Panthalassa, due to certain forces, it got drifted, and later due to discovery by Arthur Holmes and seafloor spreading theory by Harry Hess, uh, scientists have disregarded the forces that were responsible for the drifting that were set by Alfred Wegener, that is tidal force and polar fleeing force. They were not the reason for a drifting of the continents. It is the convectional current that is happening in the interior of the earth, and the seafloor spreading that is happening due to convectional current. They were the reason for the drifting of the continents and the formation of the oceans. Okay. You- um, if you are confused about this, rewatch the class again in detail, and you will get a clearer picture. Okay. And make sure you keep your atlas while you are studying continental drift theory. Okay. That's foremost. And yeah, we are done with seafloor spreading also. I have explained the facts that were mentioned in 11th class geography, what seafloor spreading is actually saying. Okay. The Please try to memorize those statements. It is easy to memorize these statements in this chapter because if you know the logic behind it, it is easier. Yeah, if you come across a statement that as we move away from oceanic ridges to continental crust, the ages of the rocks keeps on decreasing. There's a statement like that, it is wrong because the age keeps on increasing towards the continent because the rocks that were adjacent to continents was much more older. Why? Because of the convection current and oozing out of the lava. Okay. Yeah. And the seafloor spreading theory is proposed by Harris, and there is a little portion I will try to explain it. Wait. Yeah. He is saying that constant eruptions at the crest of the oceans. It is crest. There is constant eruptions here. Okay. At the crest of the oceanic ridges caused the rupture of the oceanic crust. There are constant eruptions here. These eruptions caused rupture of the oceanic crust. Okay. How it is ruptured? Ruptured means these constant eruptions uh, spread at the oceanic floor. Okay. This is called crust, rupture of the oceanic crust. Okay. The sentence here says that due to constant eruptions at the crest, that is at the peak. Crest means peak or summit of the oceanic ridges. There is a rupture of the oceanic crust. Okay. The oceanic crust got ruptured. That means it got spread. Okay. And there is empty space here. Whenever the crust is separate, there will be empty space here, and this empty space is getting filled by the lava. This empty space is getting filled by this lava. Okay. And thus the ocean floor spreads. The younger age of the oceanic crust, as well as the fact that spreading of one ocean does not cause the shrinking of the other, made us think about the consumption of the oceanic crust. Okay. Consumption of the oceanic crust. I have just explained here that uh, okay, whenever a continent and oceanic plate converge, I mean continental crust or oceanic crust converge, it's not crust. As I didn't teach about plates, I am calling it as a crust. Okay. In next class, I will teach about plates. Whenever a continent and oceanic gets converge, the oceanic part subsides down because it is denser. And it this crustal part subsides down and get consumed by the magma. It goes into the magma, gets consumed by it, and again rises up. It gets consumed in the magma because magma is very hot. Okay. And this heat is generating from the radioactive decay happening in the magma or asthenosphere. The oceanic crust is getting consumed. Okay. The oceanic plate is moving towards it, subside down, getting what consumed. And again further the ocean is getting consumed, and again rising, new oceanic crust is forming. Again it is the movement is happening, again converging, again rising up, new oceanic crust is formed. Again it is this convergence happening. Okay. This convergence is continuing, and during this converging also the oceanic crust subsequent the oceanic crust is getting subsided, getting consumed, and again rising as hot magma, and again new oceanic crust is formed. Okay. This cycle of event, what I just said, is the reason uh, for is the is the reason proposed by Harry Hess, and it is the reason why uh, spreading of one ocean does not cause shrinking of the others. Okay, if we say that Atlantic Ocean is spreading, it doesn't mean that Pacific Ocean is shrinking. Okay, um, the as the Atlantic Ocean uh, is getting spreaded somewhere on other ocean, the oceanic crust is subsiding down, again rising up, and new oceanic crust is formed. Due to this cycle of event, the spreading of one ocean does not cause shrinking of another ocean. Okay, yeah. Okay, that's all for today, and we will learn about plate tectonics and about Indian subcontinent plate in the next session, and after that, we will learn about interior of the earth, earthquakes, and volcanoes. Yeah, thank you.